Welcome back. So, we've put a lot of hard work into the question of how to think about various biological problems probabilistically. And I'm excited now to try to talk to you about an actual sort of serious substantive case study in probabilistic thinking. And part of the flag under which we will fly this particular vignette is the idea that models and words have consequences. And when I say models have consequences, what I mean by that is that if we work out the implications of a given theoretical model of some phenomenon, we may be surprised to find that the subtle and nuanced implications of the original model are something that maybe we didn't expect. And I'm being a little bit intentionally vague because that will come up in the context of the problem that I'm going to think about now. So the general topic is, if you like, is bacterial size control, or more broadly, cell size control as a bigger umbrella topic, although the primary focus will be on bacterial size. Let me, though, sort of fast forward and show you. This is from the group of Fred Chang, and these are fission yeast cells. And the thing that's being reported here in the lower left is the probability of finding cells of a given size at division. In other words, at the moment of division, one asks the question, how big are you? And then you do that for a bunch of cells, many cells, and you plot a histogram. And what you see, the reason I wanted to show you this image is just to give you a sense, this is something you can do with a microscope. And for the case of bacteria, this is from the work of Christine Jacobs Wagner, and there's a really nice paper, maybe 2014. I think the first author is Campus. It's in Cell, and what you're seeing here is the length at division and the length at birth. And the thing that I want you to appreciate, this is our moment of flying over the glaciers of Greenland. We want to not take it for granted. We want to hold it up as mysterious and as profound. Is that in a population of cells, that their size is well maintained around some very specific average length or average volume. And so what we're going to do is we're going to try and explore several hypotheses for how that can be achieved on the grounds that it's not obvious. So what we're going to do is we're going to talk about three categories of models that have these kind of pithy names. There's the timer model. So in the timer model, each cell grows for a constant time, and then it doubles in volume, basically, and that leads to a mechanism of cell size control. Although we'll have to see what the implications of such a model are. The sizer model is the idea that the cell grows until it reaches some critical size for cell division, and then it divides. And that's actually what I just showed you in the case of yeast. I will come back to that a little bit just to demonstrate experimentally what one would expect in a sizer model. In fact, let me not play games. Let's actually just look. So it's shown over here on the right, which is a really brilliant way of plotting the data. So what is the idea? If you're a sizer, if you grow until you reach a critical size, then the amount of volume that you add will be dependent upon how big you were at birth. The bigger you were at birth, the less you'll add, because to get to that critical size takes less mass. And so what you see here is this beautiful correlation for both the wild type cells, which is in red, and the two different mutants, that the added volume basically scales, or I should say, as the cell at birth is larger, the amount of added volume goes down. So the slope of this thing actually would tell us about the nature of this sizer mechanism. And then the last of the models shown on the right is the so-called adder. And the idea of that one is that the cell adds a certain amount of material, and once it's added that amount of material, it will divide. What's shown on the left in the bottom is basically just a demonstration of what these models will do over generations in terms of trying to understand the what do I want to say, the time evolution if you start off wrong in terms of the volume. And then the part D shows you when I say models have consequences, it shows you the consequences of these three different models in terms of the relationship between the delta V, the volume added, and on the x-axis is the size at birth. So as you see, the adder model basically predicts that if you're going to add a constant volume, it doesn't matter what your size was at birth because you're going to add a constant volume, and that's it. So, three very different scenarios. And what I want to do now is I want to give a sketch, and I think maybe rather than writing everything out, I will walk you through what I have already written out because I think there's a lot of sort of technical details here, and it seems like maybe it got frozen. Shoot. Okay, so sorry I've gotten disconnected again, so I've got to reconnect. So I ask your patience while I do that. Life in the pandemic has many issues, and one of them is some of the technical challenges just of pulling off this remote teaching. Okay, so here's the concept. The concept is that the cell on the left starts out with a certain mass, which I'm going to call m birth, the mass at cell birth. And in the timer model, what's going to happen, first of all, I want to make the observation that during the cell cycle, the mass grows exponentially. So m of t, shown here, is equal to m birth times e to the lambda t, where lambda is the growth rate. And what happens is after a time tau, which I'm going to call the birth time, or the timer time, then we will make two new cells, each of which has a mass m division divided by 2. And how do we know m division? Well, m division, as shown here, is m birth times e to the lambda tau, where tau is the tau of the timer. So the key assumption that's going to be made in this analysis is that indeed there is this timer tau, but in addition there's going to be statistical fluctuations, and I'm going to use this squiggle C letter as a way of representing the statistical noise, the little variation. This is going to be drawn from a Gaussian distribution, for example, and this is the little bit of error in tau at each generation. So what we're going to do is we're going to write down a recursion relation. We're going to find the relationship between the birth mass in generation n and the birth mass in generation n minus 1. How do we do that? Well, I take the birth mass at division n minus 1, I propagate it forward in time, e to the lambda tau n minus 1. That is the division mass. This is m div to the n minus 1 or n minus 1 label. I take a half of that. So that tells me the mass at the nth generation at birth. Now let me take the logarithm of both sides of this expression. I take the logarithm of both sides. I get log of m birth at generation m, log of a half. I have log of m birth n minus 1, and then plus my tau n minus 1. And now I use my definition from above of tau, shown right here, and I plug that in, and so I'm left with, the net result is I'm left with these two terms, log of m birth at n minus 1. So log at m birth at n is log of m birth at n minus 1, but then plus this correction, or this error, that has to do with the noise. Now I'm gonna define y sub n as an algebraic quantity that we're going to keep track of, and that's equal to the logarithm of m birth at n. So this is basically a nonlinear transformation just to introduce a new variable, and this is going to simplify the notation for our recursion relation. So I can rewrite what I just said, which is that the nth generation division mass is related to the n minus 1th plus this error term. Now I'm just going to keep on propagating this. In other words, I'm going to just keep on repeating the same structure because I know that yn minus 1 is equal to yn minus 2 plus lambda squiggle n minus 2. So I can just keep on propagating down the line like this. And what I'll be left with at the very end is shown here. Okay, so the mass, basically the logarithm of the mass in the nth generation is equal to the logarithm of mass in the 0th generation, plus this interesting statistical feature which tells me that I've accumulated some errors in each generation. Now, we want to take averages. When I say take averages, what I mean is we're going to average over all the possible ways that those noises could have occurred, and we're going to use the notation throughout the course of these angular brackets. So, when I write this, it means average of ... And so what I see here is that the average mass in the nth generation is equal to average mass in the 0th generation, not surprisingly. And the reason is because the average of the noise is 0. I said that we were going to draw the noise from a Gaussian distribution, for example, which has 0 mean. And so that's the nature of the averages. But what about the variance? In other words, if I want to get a measure of the fluctuations, I need to actually compare the variance to the average squared. So to write out the variance is basically going to come from taking the average of yn squared. So I plug these pieces in. In other words, I just use the definition of yn, put it in twice, and I note that these noise terms, if squiggle I and squiggle j are the same, in other words, if I look at the noise for the same instant, so let me just say what I mean by this. When I multiply all these out, I'm going to have epsilons, there's squiggle 0 times squiggle 0, I'm going to have squiggle 0 times squiggle 1, squiggle 0 times squiggle 2, and so on. And I'm going to accumulate a bunch of these terms, ci, cj, which you see right here, and only for the case where I is not equal to j do they survive. So that leaves me with this result. Now, the statistics is such that each one of these has the same value. These are all drawn from the same Gaussian distribution, which has a width sigma squared, but I have n of them. So what I found is that the variance, yn squared, is equal to y0 squared, but then plus this accumulation, and the really important observation is that the error grows with n. In other words, the variance grows with n. So over time, that means that this distribution is going to get wider and wider and wider, in contradiction with the result that I showed you from Christine Jacobs-Wagner. So I can now, the way I think of this is I know the first and second moments of this distribution, and so I can write the probability distribution. I'm kind of using a maximum entropy worldview, the way that Janne Kondev, who is one of my book co-authors, he thinks of it differently. He would use the central limit theorem, but I'm kind of amused with thinking of this in a maximum entropy language where I know the first and second moments of the distribution, and therefore I can say that that my best guess for the distribution is that it's a Gaussian. And so the conclusion is that I basically have a log normal distribution, meaning that the probability of the log of n is a Gaussian. So we're left with this super interesting result, which I show you right here, which is that the sizes are log normally distributed, but most importantly, there's this n right here, which means that the width is going to get larger and larger as n gets larger and larger. So the more generations in we go, the larger the fluctuations. And so, so this fails the test of size control that we were kind of looking for when thinking about the timer, the adder, and the sizer models. So what we'll do in the next vignette is I will talk about the adder model and show that it actually has bounded fluctuations. and then we'll return to the data from Christine Jacobs Wagner and her team, just to see that it also satisfies this notion that the amount of mass should be independent of the mass at birth. So that's where we are in this, and I hope you enjoyed that little case study.